Good to be with you once again. Today we are going to talk about directional derivatives and the gradient. Quick preview, the directional derivative is the slope in some arbitrary direction. The gradient is the direction of steepest ascent. Directional derivatives and the gradient vector. Directional derivatives. In a previous lesson, we talked about the tangent plane. To come up with the equation of the tangent plane, we considered two curves on the surface, C1, the intersection of S and the plane y equals y naught, and C2, the intersection of S and the plane x equals x naught. Then we found the tangent line to these curves. But why did we pick these? So just a reminder, once again, C1, the intersection of S and the plane y naught, would be this intersection line in the first picture. And C2, the intersection of S and the plane x equals x naught, would be this intersection curve, the green one, in the second picture. And then we found the tangent lines to the curve. So that would be this tangent line, and I think a little hard to read through here, but looks like it'd be like that tangent line there. So we have our tangent lines, and we have our curves, and we have our intersection. But why do we pick those? We could have chosen from, instead of choosing these particular red tangents, we could have chosen any of these dashed tangent line or curves of intersection. So why choose these particular ones? Well, we talked about how we picked them because they're easier. Well, the real reason that we picked them is because we only knew how to take the partial derivatives of a function with respect to our main axes. So that is with respect to x and y. In this section, we're going to define partial derivatives of a function in other directions. Recall the first homework problem you had in 14.3. The question asked you to find the partial derivative of f with respect to x at 2, 1, and the partial derivative of f with respect to y at 2, 1. Well, what is the meaning of these notations? Let's give the function a story. Let's say that z equals f of xy is representing the surface on a 3D mountain. So z is the height. The partial derivative of f with respect to x at 2, 1 gives you the rate of change of height in the direction of x. That means how fast or slow your height or slope changes as you walk in the direction of the positive x-axis or parallel to the x-axis, passing through the point 2, 1, 10. And the 2, 1, 10 was given in a previous question. With our current knowledge, we can only find the change in height walking in the direction of positive x, that would be east, and walking in the direction of the positive y-axis, that would be north. But there's so many other directions. What if I wanted to walk in the direction northeast? Directional derivatives will help us with that. We generally use a unit vector to show the direction because we don't want the length of our vector to influence our perspective of the rate of change. To understand that, think about running versus walking in the direction of northeast. That may influence your perspective of how fast the height of the mountain changes, the speed of 1 unit of distance per unit of time. Let's talk about the question where we were looking at the partial derivative at the point 2, 1. So here would be, in our picture, here would be our x-axis, and here's our y-axis, and the point 2, 1 would be right here. Notice it is indeed on the contour line of 2. And so our question is asking, what's going on if we look at the partial derivative in the x direction? Well, that would be asking for the slope as we move from the red point in the direction of the blue line, because that would be this direction. Or you could have the slope in the y direction. That would be the slope going vertically, so east or north. And then the question also asked, well, what would happen if we wanted to travel northeast, say in, I guess I could make that the red direction. So northeast would be like going in this direction to the northeast. And so you might look at it and go, well, if we went in the northeast direction, then we're traveling almost exactly along this level curve. And it sort of gives us a hint of things to come. But since we're traveling along the level curve, we would just estimate that there is no change in height. So maybe our directional derivative in that direction would be 0. Back to our derivation. Let z equal f of xy. We need to find the partial derivative of this function in the direction of the unit vector u, which is ab, that lives on the xy plane at the point x naught, y naught, z naught. Correct a typo here, in the direction. So let L be the line in the xy plane that is parallel to u and passes through the point P naught, which is x naught, y naught. This line can be represented by the parametric equations x equals x naught plus TA and y equals y naught plus TB, where T is an arc length parameter with its reference point at P naught, which is x naught, y naught, and the positive direction is in the direction of u. Let's see if we can help ourselves with our picture. So we have our u vector here showing up. And we have our line L. Where is that? Our line L. And that's this whole line all the way. Okay. And we know that that line can be represented, that line L can be represented parametrically as follows. That little bit about the arc length says that when t equals 0, we've traveled 0 distance. When t equals 1, we would have traveled a distance of 1. When t equals 2, we would have traveled a distance of 2. So time and distance are the same. It's sort of like traveling at 60 miles an hour. So at 60 miles an hour, if you've traveled for 5 minutes, it's like you've gone 5 miles, or 10 minutes, you've gone 10 miles. So that works at 60 miles an hour. It doesn't work at 35 miles an hour. Okay, so continuing on, as t increases, the point P of xy, so this is this point here, P of xy moves in the direction of u along L, and a companion point Q with z coordinate z equals f of xy equal to f of x naught plus ta, comma, y plus tb moves directly above or below along the surface, tracing out the curve. So let's see if we can get the 3D in here. So notice that this line L lives in 2 dimensions over here in 2D, but it also lives in 3D, and line L is on the XY plane. And so when you're at P naught on the XY plane, that translates to this point above. Similarly, the point P translates to the point Q above. Okay, and so just like there's the red line on the XY plane, it translates to a slice or a line along the surface, z equals f of xy. Let's look at a manipulate to try to better understand how we could intersect a surface with a plane and find slopes along that. All right, here we are. What I'd like to point out is that we have our point below, is our point AB, and that point translates to a point along the surface, and different points, AB will give me kind of different lines, and then we can have a vector u that is on the xy plane. So here it is on the xy plane, that's this blue vector. And that vector u is somewhat arbitrary, right? We could change its direction. And when we change that direction, what we are doing is we're saying start with the given point, which is up here. So this is given. And then we're going to move along a direction of travel. Here's our U. It's our direction of travel. And what we're wondering is if at that given point in that direction of travel, if we looked at a tangent line along that, we could ask ourselves, what is the slope of this line? That slope is going to be what we call our directional derivative. So once again, you pick a point, you pick a direction, you have the point in the direction, you can ask what's the slope at that point in this given specified direction. The rate of change of z with respect to t can be calculated using the chain rule. So we could think about our little tree diagram. So you could have f being a function of x and y are functions of t based on the parameterization above. And so we would have the partial derivative of f with respect to x, that's here, times partial derivative of, the derivative of x with respect to t, that's there, partial derivative of f with respect to y, that's here, partial derivative of y with respect to t, that's there. That's coming straight out of the chain rule. And note that since x equals x naught plus ta, and y equals y naught plus tb, then this tells us that our x of t is equal to a, and our dy dt is equal to b, right? Because of what's given. And so our formula simplifies a little bit to dz dt equals fx times a plus fy times b, where x and y are expressed in terms of t. But p naught at x naught, y naught is a point on L corresponding to t equals 0. And so we could actually evaluate there. And so we get the dz dt when t equals 0 would be indeed fx at x naught, y naught, a plus fy times fy of x naught, y naught times b. This quantity is called the directional derivative of f at x naught, y naught in the direction of u. And we could use other notations such as the directional derivative of f in the direction of u at x naught, y naught. There's a typo here. Let me see. What's this typo? Let's see. Quantity is called directional derivative of it in the direction. Other notations. I know this should be a lowercase c. And this quantity is called, oh, right here, the directional derivative. Note, if u is in the direction of the positive x-axis, then u equals I, which is 1, 0. So we get the derivative of z with respect to t at t equals 0 equals fx at x naught, y naught. That is the partial derivative with respect to x. And if u is in the direction of the positive y-axis, then u equals j, or 0, 1. So we get dz dt at t naught equals f of y at x naught, y naught. That is just the partial derivative with respect to y. That is, the partial derivatives with respect to x and y are just special directional derivatives. Again, there's a couple of missing words. Is in the direction of the positive x-axis, is in the direction of the positive y-axis. So here's the key. If it's with respect to I, then we just end up with fx. If it's in the direction of j, then we just get the partial derivative with respect to y. If f is a differentiable function of x and y, then f has a directional derivative in the direction of any unit vector u equal to ab. And the directional derivative of f in the direction of u at xy is partial derivative of f with respect to x at xy times a plus the partial derivative of f with respect to y of xy times b. So here's our key formula that's worth memorizing, or at least understanding. Example 1. Find the directional derivative of f of xy equal to 3x squared y at the point 1, 2 in the direction of the vector v equal to 3i plus 4j. And so we need three things in order to be able to answer this question. So the first thing we need is we need a unit vector parallel to v. Unit vector parallel to v. So that would be our u vector equal to 3/5, 4/5. Notice this is our a, 3/5 is our a, and 4/5 is our b. We also need the partial derivative with respect to x at 1, 2, which would be 6xy at 1, 2, which is, it looks like 12, and fy at 1, 2, this would be 3x squared at 1, 2, which looks like 3. And so all told, once we have all these things together, we can say the directional derivative of f in the direction of u at 1, 2 will equal 12 times 3/5 plus 3 times 4/5, or 36 plus 12, 48/5. Okay, let me make sure you're seeing your colors. So the 3/5 and 4/5, that's showing up here. That's your A and your B. And the fx being 12 is here. The fy being 3, that's there. What does this mean? This means that if you are at the on the curve, on the surface, f of xy equals 3x squared y above the point 1, 2, and if you traveled in the direction of the vector v equal to 3 plus 4, then if you traveled a horizontal distance of exactly 1, then you would go up in the vertical by about 48/5. That is the slope of the tangent line at 1, 2, I guess that'd be 1, 2, 6. No, yeah, 1, 2, 6 is 48/5. Let's look at another manipulate to try to help ourselves, again, see the picture of what's going on. All right, so here's what I want you to see. That we have some point in our example, we were at the point 1, 2, here we're at the point 3, 2. And at the point 3, 2, above that, you can see the surface. Our vector u down below gives us a direction. And so you can imagine cutting the surface with a vertical plane that is parallel to this vector, and that is going to create this black line of intersection. And then we could ask, what's the tangent line right above the point 3, 2? And the tangent line is this blue vector. And we could ask, what is the slope at that point? And in this case, it says the slope is about 2.47. So that's saying the steepness in the direction of 3, 2, the slope in the direction of 3, 2 is 2.47. That is, go forward 1, you go up about 2.5. It is worth noting that reversing the direction of u reverses the sign of the directional derivative. that is, the directional derivative of f at x naught, y naught in the direction of negative u equals the partial derivative of f with respect to x at x naught, y naught times negative a plus the partial derivative of f with respect to y at x naught, y naught times negative b. You could factor out the negative, so this would be equal to negative times the partial derivative of f with respect to x at x naught, y naught times a, plus the partial derivative of f with respect to y at x naught, y naught times b, which would be the same thing as negative the directional derivative of f with respect to u, in the direction of u at x naught, y naught. The gradient vector. The directional derivative formula can be expressed in the form of a dot product. So the directional derivative of f in the direction of u at xy is equal to the partial derivative of f with respect to x at xy times a plus the partial derivative of f with respect to y at x y times b. And you'll notice that we could write this as the dot product of the partial derivative with respect to x, comma, the partial derivative with respect to y, dotted with ab. That is, partial derivative with respect to x at xy, comma, partial derivative with respect to y at xy, dotted with the unit vector u. The first vector in this dot product occurs not only in computing directional derivatives, but in many other contexts as well. So we give it a special name, the gradient of f, and it gets its own notation, grad f or del f, which is read del f, although the symbol is called a nabla, which is a little bit confusing. So you have this one, which is a delta, and the upside down one, which is called a nabla. I don't know why, it just is. I guess we could look it up and try to figure out what's going on there. Definition. If f is a function of two variables, x and y, then the gradient of f is the vector function del f defined by del f, or gradient of f at xy, equal to the vector partial derivative of f with respect to x at xy, comma, partial derivative of f with respect to y at xy, or if you will, partial derivative of f with respect to x times the I vector plus partial derivative of f with respect to y times the j vector. With the gradient notation, the directional derivative can be written simply as the directional derivative of f in the direction of u at xy is equal to the gradient of f at xy dotted with u, where u is a unit vector. Let's look at a manipulate to begin building our intuition of this new gradient vector. All right, so the gradient vector lives in two dimensions. The surface is in 3 dimensions, but the gradient vector lives in 2 dimensions. And it's the vector at a point that is perpendicular to the contour line, and it would point in the direction of the uphill, not the downhill. So gradient points in the direction of steepest ascent. The negative of the gradient would point in the direction of steepest descent. And this is going to be a theme we're going to talk about quite a bit in this particular section. Example 2, find the gradient of f of xy equal to 3x squared y at the point 1, 2, and use it to calculate the directional derivative of f at 1, 2 in the direction of the vector 3i plus 4j. So this is just the same question as before, just asking us to use the gradient. So here we would first, again, we can find our u vector. U is a unit vector, so it will be the v vector, 3, 4. But we need to divide each of these terms by the magnitude of the vector, which is 5. So 3 over 5, 4 over 5. It's our vector. And 2, we can find our gradient vector. This is a vector quantity. You can put an arrow over the top of it if you want to, but you don't need to, simply because the fact that it's a gradient tells you that it's a vector. So this would be 6x, y, and 3x squared. That's the gradient field. We'll talk more about fields in chapter 16, and we want to evaluate this at 1, 2. And that would be at 1, 2 would be 12, 3. And so this tells us that our directional derivative in the direction of u of f at 1, 2 would be 12, 3 dotted with 3/5, 4/5, which would be 36 plus 12, or 48 over 5, just like before. So same exact process, it's just a little bit easier or more concise to write that directional derivative when you're using that gradient notation. For functions of 3 variables, we can define directional derivatives in a similar manner. Again, the directional derivative of f in the direction of u, f at the point x, y, z, can be interpreted as the rate of change of the function in the direction of a unit vector u. Now u lives in 3 dimensions, and we can calculate that directional derivative of f in the direction of u at x, y, z as simply being the gradient of f at x, y, z dotted with the unit vector u, just like before. Example 3. Find the gradient vector of f of x, y, z equal to x squared y minus yz cubed plus z at the point 1, -2, 0, and use it to calculate the directional derivative of f at the point 1, -2, 0 in the direction of the vector 2i plus j minus 2k. So first thing we're going to do is we're going to find our u. And so u is going to be 2, 1, -2, and then we need to divide by the magnitude, which would be square root of 4 plus 1 plus 4, square root of 9, or 3. So our u vector is 2/3, 1/3, -2/3. Second, we need to find the gradient of f. This will be, looks like 2xy, and then x squared minus z cubed, and with respect to z, minus 3yz squared plus 1. And we could evaluate this at 1, -2, 0. So let's see, that would be 2 times 1 times -2, so that'd be -4. And 1 and 1. Oh, that's supposed to be I have it written as a point. This should actually be a vector, not a point. So this should be angly vector because it's a gradient. And so 3, we can find our directional derivative. So thus, the directional derivative of f in the direction of u at this point, 1, -2, 0, will equal -4, 1, 1, dotted with 2/3, 1/3, -2/3, which would be -8 plus 1 minus 2, 9 over 3, which is just 3. So this is telling us that the slope So this, what does it mean? It means the slope, thus the slope of f in the direction of v at point 1, -2, 0 is 3. So if we traveled along, and that'd be slope, because now this graph would live in 4 dimensions, right? Because it's got 3 variables. So if we traveled along that vector a length of 3, then we would go up in 4 dimensions, 3 units between the two, from 1, -2, 0, along the vector 2, 1, -2. The gradient is not just a notational device to simplify the formula for the directional derivative. The length and direction of the gradient del f provides important information about the function. For example, suppose z equals f of xy is representing the surface of a mountain. That is, z is the height at xy. If we want to know in which direction f is steepest and what that rate of change is, we need look no farther than the gradient vector. Let's see how. So let's write the dot product for the directional derivative of f in the direction of u. So we know that directional derivative of f in the direction of u can be written as the gradient dotted with the u vector. We could now rewrite this using the angle between the two vectors. So remember, there's 2 versions of writing the dot product. So this would be telling us that this thing is equal to the magnitude of del f times the magnitude of u, which is 1, by the way, times the cosine of the angle between the 2 vectors. That was our alternate definition of the dot product. What's the magnitude of u? U is a unit vector, so this is just a 1. So we could rewrite this. This tells us that partial derivative of f in the direction of u equal to the magnitude of the gradient of f times the cosine of theta. What's the maximum value of cosine theta? Well, we know the maximum value of the cosine theta, max cosine is 1, and it happens when theta equals 0, or 2 pi. So if theta equals 0, what is the relationship between the gradient and u? So this would be saying that the gradient and u are in the same direction. They are in same direction. So what can we conclude? We can conclude that the maximum gradient is when the maximum gradient, let me phrase that again. We can conclude that the maximum directional derivative is in the same direction as the gradient. So the gradient is in the direction of max directional derivative. So this is captured in this theorem. Suppose f is a differentiable function of 2 or 3 variables. The maximum value of the directional derivative, that is, the directional derivative of f in the direction of u, is the magnitude of the gradient of f. And it occurs when u has the same direction as the gradient vector del f. Example 4. Go back to example 3 and find the maximum rate of increase of f at point P. So let's remind ourselves of what's going on. So I think that f of x, y was, oh my gosh, like 3x squared y. Example 4. Go back to example 3 and find the maximum rate of increase of f at point P. So recall that f of xyz was equal to x squared y minus yz cubed plus z, and P was the point 1, -2, 0. So if we want to find the maximum rate of increase, that means we need the gradient. So that means we need gradient of f, which is itself a vector field. We'll talk more about vector fields later on, so we don't really need to worry about what they are quite yet. So first we need to find fx. So that would be the 2xy. And then we need to find fy. So fy would be 2, x squared minus z cubed. This is a square that looks a little suspiciously like a 3, comma, and the partial with respect to z, that would be minus 3yz squared plus 1. So we've found our gradient, and we want to specifically find this at the point 1, -2, 0. We've already done this. By the way, this is a little bit of a repeat question. And so that will be at 1, -2, so it'll be -4, comma, 1, comma, 1. So we've found our gradient vector, and if we want to find the maximum rate of increase, that means that what we need is the magnitude of this gradient. Which would be equal to the magnitude of that vector, -411, which is square root of 18. And so this is saying that if you were at the point, like on the surface above the point -1, -2, 0, then there would be lots of directions you could travel, but the fastest your slope could change would be square root of 18. We could give ourselves a little bit of a reality check on that by comparing. So when I say comparing, I'm saying we can check. This is the max rate of change. And then previously we found in another direction, we found that the rate of change was equal to 3. And sure enough, the 3 is less than that maximum rate of change, right? So here, what am I trying to say? I'm trying to say that it's less than this right here. Is less than the gradient value. Oh, magnitude. Trapped. Or snargled my thing. There. Example 5. For the function f of xy equal to x squared e to the y, find the maximum value of the directional derivative at -2, 0, and give a unit vector in the direction in which the maximum value occurs. So this is sort of a variant on the question that we just answered. So since we were wanting to do something with maximum value of the directional derivative, again, first we're going to start by finding our gradient. So our gradient will be equal to the partial with respect to x, which is 2x e to the y, comma, partial with respect to y, which is x squared e to the y. And in this case, we are continuing to evaluate at a given point. So we care about this at -2, 0. So that would be, looks like the vector -2 times -2, -4 times e to the 0 is 1. So -4, comma, 4. So here we've found the gradient. We now want to find the max rate of change. That would be the same thing as the absolute value of that gradient. Or in other words, the square root of, looks like 16 plus 16, or square root of 32. So this is our maximum rate of change, the steepest the directional derivative would ever be. And it leads to a logical question, which is, what's the direction that will happen in? So if we want a unit direction in the direction of the maximum value, then we're going to look at our gradient vector. This is going to be our v. And now we've got to find a u that's in that same direction. So we could take this vector and divide by its magnitude, which is square root of 32. So that tells us that u will be -4 over square root 32, comma 4 over square root 32, which simplifies to u equal to -1 over root 2, comma 1 over root 2, or the familiar root 2 over 2's from trig, if that helps. So this is the direction of the maximum increase. Max increase. The gradient vector and contour plots. So question, what happens to the height of a function, the altitude, as you move along a level curve? So moving along a level curve, that would be moving along one of these level curves in the plot. Remember, the level curves correspond to places where the height does not change, right? So what happens to the height of a function as I move along a level curve? Nothing, right? The height remains constant. Is constant. It's a level curve, right? That's why the name. Question, where is the gradient on a contour plot? Well, the gradient is in the direction of greatest change. And so if the level curves represent where there's no change, it should be reasonable to think that there's going to be greatest change if we are perpendicular to the level curves. So the gradient is always going to be perpendicular to the level curves. And you'll notice that there's actually two vectors that are perpendicular. You could go, you could sort of aim in or aim out. And we're going to choose the one that's aiming in. And the reason is because the gradient is going to be uphill. So it's going to be perpendicular to the level curves and in the direction of steepest ascent. Ascent, that's up. Oops. All right, let's look at a manipulate to try to see this again. All right, I want to remind you that the level curves live in 2 dimensions. So the surface is in 3 dimensions, level curve is in 2 dimensions. It's down here, corresponds to a place on the surface where everything is the same height. And you'll notice that the blue line, let's see if I can get my colors right. Here, this would be my gradient. And it's in the direction of steepest up. Oh, that makes sense. It's kind of pointing out. That would be this direction here. The red vector would be the negative of the gradient. That's the steepest descent. That would be pointing down. And the 2 black vectors, these would be along the contour line. And those would be represent where there is no change, right? So the red is going down, the blue is going up. It's the direction of the gradient. The black ones along the level curves would represent no change at all. I think I can do this in other locations. So here's another point, okay? And at this point, notice up would be kind of here to the left, and sure enough, blue vector is pointing up and to the left, down, kind of to the right. That's the red vector, that would be the opposite, and the black vectors are along the level curve. Those would represent no change at all. Third point, let's see, come on. Third point here, again, the blue vector, which is pointing up, kind of here it's going kind of out, would represent going up the surface. The red one would pointing kind of back to the left, be representing going down in the surface, and the black along the level curve would represent no change whatsoever. From this, we can make the connection that F has a maximum rate of increase in the direction of the gradient and a maximum decrease in the opposite direction, and no change when orthogonal to the gradient. That'd be along the contour lines or the level surface. So I'd like to look at 3 topographical maps to try to help you build some intuition of this. And so the first of these topo maps is right here of our very own Highline College. So in case you're wondering where we are right about this point here. That's us for our class. Okay. And so if you look at the contours here look something like this. It's a little hard, a little bit difficult to see. Okay. And you might say, well, what does that represent? Well, what that represents is that and this is going to blow all your minds, it represents the fact that Highline College here is on the hill, right? You've got all of these contour lines showing up. It's not a super steep hill. The lines aren't really close together, but it's on a hill. And what does that hill do? That hill slopes all the way down to the water. Okay, so it's on a hill. Where's the gradient showing up? Well, the gradient would be perpendicular, kind of pointing to the right. And you can see that, like, oh, at Highline College, if you go due east, you're walking straight up the hill. That's the steepest path. If you walk north-south, that's when things tend to be flat. You might also notice in this picture that if we move into the city of Des Moines, you can see other contour lines. And you'll notice that those contour lines are in other directions, and that represents the fact that there's another hill that's happening in the city of Des Moines. Furthermore, if you jump over into the city of Kent, you'll notice that in Kent, there are almost no, there's no contours down here, or no really obvious ones. Why is that? It's because you're in the valley. You're in the flat valley. So since you're in the flat valley, there's no elevation change, so there isn't going to be a lot of contour lines. So let's think about this idea a little bit more with peaks, ridges, valleys, and the path of steepest ascent. And here is a topographical map at Mount Rainier. And so let's start by talking about peaks. And so if we want to look for peaks, you're looking for high points on the graph. This isn't the actual top of the mountain. This is just a part of the mountain. And what I want to point out is that when you have that little circle there, that little circle is going to represent a peak. So that smallest circle. It could also be a valley, like a bottom of a hole, but because it's labeled with the highest number, we know that it's a peak. So peaks, those are the little spots. We could look at like holes. Notice that you have Reflection Lake. It should come as no surprise that around a lake, you have no change in height, right? Same contour line everywhere. And if we started from the lake and we could ask, where would the steepest ascent take me? I could go from the lake and just kind of pick a direction. Maybe we'll go this direction, some down here from Reflection Lake, and I want to cut across the next contour, but I always have to be perpendicular to the contour. So it looks like I'm going to go there, and then if we want to keep going, it looks like we could keep going up. So I'm trying to go with steepest ascent. Okay. And it looks like the next one up is in this region, and we want to be able to cross it, but we've got to be able to be perpendicular. So we're going to have to then make some sort of a curve. We could go straight, but that'd be a little weird. So we'll probably be here. And now it looks like we're kind of perpendicular. Looks like we're going to cut around. Well, it looks like we managed to choose a point that's going to, hard to tell what's going on here. It's going to go all the way from Reflection Lake all the way to the top of this little peak. Okay, so that would be a path of ascent. So it's always the steepest path, if you will. They tend to be along to go along once you make it, they tend to go along ridges. Maybe we could try a different path and see where a different path would take us. So if we started off maybe here kind of going into the going through the sea and reflection. We're going to stay perpendicular. This is a little bit hard to see. So always want to make sure that I'm perpendicular to the um, contour lines. I think I got to keep going up. Sometimes it can be a little tough. You have to read the values and go, this is 5,400, this is 5,200. So I'm going up. It looks like I'm still going up the mountain here. That would be my path of steepest ascent. So they tend to be kind of work their way toward ridges, if you will. A valley is going to take you out. Oftentimes it'll want to leave the valley, whereas the ridge it'll take you to the ridge, like, because a ridge is like a high point, a valley would be a low point. So there's a couple of things along Mount Rainier. Let me see if there's anything else I want to point out. Oh yeah, how about this? Notice that over in this region, the contour lines are very close to each other. So that would be a place where the graph is very, very steep. Whereas, shockingly enough, the flattest places are the places right around the lake. So it's flat near the lake. It's steep over here, steep next to Narada Falls. Narada Falls is beautiful. If you ever get a chance to go, make sure you stop in and take a look at the waterfall. Very beautiful. Example 6C, this is our third and last topo map. So consider the contour plot or topographical map of the crater of Mount St. Helens, where z equals f of xy and gives the altitude in feet at point xy, where x and y have the traditional orientations. The solid black line shows the level curve at 6,000 feet. So that would be this one right here. All right, so I'm guessing you probably all know this, but in case you don't, let's see. Oh, I wonder if we could even find a picture of a video of Mount St. Helens blowing. Let me pause and see if I can find that for you. This is just a few hours from where we live, and so I thought I'd show you. So this is 1980 between us and Portland. Here's the mountain. Used to be a beautiful mountain, getting ready to blow. This is a time lapse. The cloud cover. This is about a 4-minute long clip. Maybe you've been there. I got a chance to hike with my family. Like when I was your age, we got to go to the ridge. Pretty crazy volcano. Just in our deck. Oh my gosh, then it blows up. So, whoa, top of the mountain. Go on. Hard to see through all the clouds. What's going on? I love those time lapses of a volcano exploding, right? A lot of crazy things happening. Lots of clouds, lots of explosions, no mountain visible. Whoa. Peak there at the mountain. Oh my gosh, the entire top of the mountain is now gone. So there's a crater. Here, mountain used to be like this. Out here, there's a crater right there. Stars. Gotta love the red things. Time lapse still going. Love that time lapse. What do you think that is? Stars? Are those planets? Burning things flying in the air? halfway through the video, so daytime again. The beautiful mountain is a national historic site. You can see here's that crater and a sharp ridge showing up in the topo map. And if you haven't had a chance to go, it is one of those amazing sites not that far from us. I was there when I was a kid, probably within a year or so of the explosion. It was ash everywhere. There was nothing alive, dead trees everywhere, blown over. Pretty crazy stuff. Today when you go, it's a beautiful, still plenty of signs of the volcano. The trees have all grown back, and it's quite lush and beautiful today. Nothing like it would have been when it exploded. Still going. One more minute left. Can't remember the exact number, but there were a number of people that died in this eruption. The ash flew halfway around the world, but just sort of depended on if you're upwind or downwind. So I think here in Kent, we would have just gotten a little bit of ash, but if you're in Eastern Washington, you would have gotten buried in ash. All right, so here we have the topo map of Mount St. Helens. You'll notice that you have the really steep, like the contours are very close together in this area. That's the edge, the inside part of the crater where it's really steep. Then you have it being flat in the bottom of the crater. And then on the outside here, this is kind of like the outside, the old edge of the mountain part is in the purple. So there's some questions. Let's see if we can answer our questions. Okay, so question number one, or A, I guess. On the contour plot, clearly marked with a diamond, the points of the level curve, f of xy equals 6,000, at which f of x is greater than 0 and f of y is equal to 0. So we want to be here, and we want to know where f of x is bigger than 0 and f of y is equal to 0. So this would mean there's no change. This means, when I think about it, this means, how do I write that? Like no change in the y direction. So if there's no change in the y direction, this means that our contour line is going in the same direction as the y, right? Because here we would have our normal orientation xy. So no change along the contour line vertically. And then in the x direction, it says we want to be going up left to right. So we want to be increasing. So let's start by looking at these points. So if we want no change in the y, places where it's vertical, maybe in this place over here, and here, and here, and there. So those are all examples of places where the contour line is straight up and down, and so there would be no change in the y direction. But we also want it to be where we're going up, left to right. Notice we're in the mountain, or sorry, in the crater. And so we would be going up, as we go from the crater out to the right, or up as we go to the left, or up going down to the bottom. And so you'll notice that these points on the right would all be kind of like as we're going down into the crater. And so the only one of these where we would be going up, left to right would be here on the right. And I think we were asked to mark it with a diamond. So I'm going to put a big old diamond over in that spot. Okay. The second question asks us, on the contour plot, clearly mark with a heart the point or points of the level curve of f of xy, f of xy equals 6,000, at which the point or the slope is the shallowest. That is, the gradient is the smallest. And so we're looking for where it's flat. And so notice that it's going to be steep over here because the contour lines are close together. It's going to be steep over here, again, because the contour lines are close together. It's going to be flattest here inside the crater. And so we're looking for the flattest of the flat spots, and that would be where the contour lines are the farthest apart. So it looks like they're the farthest apart, maybe in this region here, or maybe in this region there, somewhere kind of like right at the base. And notice my contours seem to be pretty far apart. There. And lastly, we are asked to begin at point A and clearly sketch the path of steepest ascent. So steepest ascent, let's zoom way in to see if we can understand what's going on. So again, we're going to go perpendicular to the curve, perpendicular to the curve, perpendicular to the curve. Notice it looks like my curve is bending a little bit. Looks like I'm bending. I'm about to cross that 6,000, and you can see me starting to go up. Okay, I'm headed up the mountain towards the steep cliff. It looks, it's not an exact science, but at any point, it should be pretty clear that we're perpendicular. Notice there's almost like a little bit of a curving that's happening back. Towards these bumps. It looks like there must be some sort of a ridge right here that we're going to keep climbing, which is pretty crazy. We don't even know what this looks like, and we're able to find this ridge. Okay, and then something weird happens right here. It's a little hard to tell, but notice there's another ridge. So we're not quite sure, but we're going to guess that we're going to take a hard turn to keep going up the ridge. And what's pretty crazy is that without even knowing what we're doing, we just ended right here at 8180 at one of the steepest points along the edge of the crater. Without even looking ahead, we were able to take that path of steepest ascent and end at one of the high points, which is pretty dope. So I really do like this picture. I think that Mount St. Helens is totally rad, and And so I love to ask questions about Mount St. Helens and topo maps on tests and assessments. So I'd encourage you to check these videos out, watch them carefully, and then also feel free to check out the many resources that are on the internet for how to read a topo map. Our last objective in this section is to establish a geometric relationship between the level surfaces and the gradient of a function of 3 variables. So suppose we have a function w equals big F of x, y, z, which lives in 4 dimensions. If we let k represent a constant, then big F of x, y, z equals k is a level surface of our function, which lives in 3D. So the overall thing's in 4D, but the level surface is in 3D. We call this surface S. Let C be a curve lying on S. I think it's lying, not laying. Lying on S. Since C is a space curve, we can define it by the vector function r of t equals x of t, y of t, z of t. And since C is on S, we can also write big F of x of t, y of t, z of t equals k. Like both of those things would be true. So assuming everything is differentiable, we can differentiate both sides of this equation. Here we're using the multivariate chain rule. And so we get, so we started with this thing. The k is going to translate to the 0. And then the multivariate chain rule gives us, let's see, make sure we see what's going on. You're saying that f is a function of x, y, z, which are in turn functions of t. And so we have the partial derivative of f with respect to x times dx dt plus partial derivative of f with respect to y times dy dt plus partial derivative of f with respect to z times dz dt equals 0. And we recognize the gradient showing up here. And so these first terms, those are all part of our gradient of big F, which is the partial of f with respect to x, comma, partial of f with respect to y, comma, partial of f with respect to z. And then we have the second terms, the dx dt, dy dt, dz dt. Those are showing up here in r prime of t, which is dx dt, comma, dy dt, comma, dz dt. So this equation can be written as the gradient of f dotted with r prime of t equal to 0. And this tells us that the gradient of f is perpendicular to r prime of t. So continuing on, if we let p, which is x naught, p, the point x naught, y naught, z naught, be a point on C with position vector r of t naught equal to x naught, y naught, z naught vector, then the gradient, so here's our relationship. We know that r prime of t is always perpendicular to the gradient. So in particular, so this is true for all t. For all t. So if it's true for all t, it must be also true for t naught. So this equation says that the gradient vector at p, gradient of f at x naught, y naught, z naught, is perpendicular to the tangent vector r prime of t naught to any vector c on S that passes through p. Huh, there's a lot of stuff going on here. So we're saying the gradient vector, let's see, gradient vector, which would be this one, is perpendicular to the tangent vector, which is this one lying on the curve. So if the gradient of f at x naught, y naught, z naught doesn't equal 0, we can define the tangent vector to the level surface, big F of x, y, z equals k at p, point x naught, y naught, z naught, as the plane that passes through p and as normal vector gradient of f at x naught, y naught, z naught. And its equation would be partial derivative of big F of x with respect to x at x naught, y naught, z naught times x minus x naught plus partial derivative of big F with respect to y at x naught, y naught, z naught times y minus y naught plus the partial derivative of f with respect to z at x naught, y naught, z naught times z minus z naught equals 0. What is this saying? In words, like not so much with all the symbols, it's just saying that the normal vector is the gradient vector. So this is the key to the whole thing. Normal vector is the gradient. And so if the normal vector is the gradient, of course, that would give you your 3 slopes. And then you have your x minus x naught, y minus y naught, z minus z naught that you're used to having in the equation of planes. Building on that same thing, the normal line to S at P is the line passing through P and perpendicular to the tangent plane. Hence, its direction vector would be the gradient. So here, direction is in the direction of the gradient. The symmetric equations of this line would be the same: x minus x naught, y minus y naught, z minus z naught in the numerators, and partial derivative of f with respect to x, partial derivative of f with respect to y, partial derivative of f with respect to z in the denominators. Those are your slopes, if you will, in the x, y, and z direction, all evaluated at x naught, y naught, z naught. Example 7. Find the equation of the plane that is tangent to the ellipsoid x squared plus 4y squared plus z squared equals 18 at the point P 1, 2, negative 1. What is the equation of the normal line to this ellipsoid at P? So first thing we need is the gradient. So and notice that this whole thing here would be your big F of x, y, z. So I guess this is the gradient of big F, not little f. And so that will be 2x, 8y, 2z. And we want this when at point P, 1, 2, negative 1, which would be, looks like 2, 16, negative 2. And so if we want the plane, it will be 2 times x minus 1 plus 16 times y minus 2 minus 2 times z plus 1 equals 0. So here's the angles, the 2, the 16, the minus 2. Here's the point, 1, 2, negative 1. And if we want the normal line, it would be x minus 1 over 2 equals y minus 2 over 16 equals z plus 1 over negative 2. And this is the symmetric form of that particular line. Again, here's the slopes, if you will, the partial derivatives, and then we've got our shifts from the given point. So there's our tangent plane and our normal line. So now you know just about everything there is to know about partial derivatives and the gradient, and specifically the directional derivative and the gradient. And we are ready to start using these partial derivatives to start answering some interesting questions. You might guess that we would be talking about maxes and mins. It's logical, but honestly, they're kind of hard to find and not particularly valuable. And so we're going to sort of skip ahead on that and move from here into integration, where we get to study double and triple integrals, which is honestly a pretty good time. So I'm looking forward to catching you on the next video, but also hope you enjoyed this little epic contribution.